Herkese merhabalar. Bugün Nano Open Webinarımızın konuğu Koç Üniversitesi Yüzey Teknolojileri Araştırma Merkezi KUYTAM Direktörü Doçent Doktor Uğur Ünal. Hocam hoş geldiniz.
Hoş bulduk, merhabalar.
Uğur Hoca, Elektrokatalitik Uygulamalar için Yüksek Entropili Alaşımların Tasarımı hakkında konuşacak. Webinarımızın webinar İngilizce dilinde olacak. Soru cevap kısmında sorularınızı İngilizce veya Türkçe yöneltebilirsiniz. Sözü ve ekran paylaşımını Uğur Hoca'ya devretmeden önce hakkında kısa bilgi aktarmak istiyorum. Uğur Ünal, doktora derecesini 2004 yılında Japonya'da Kumamoto Üniversitesi Uygulamalı Kimya ve Biyokimya Bölümü'nden aldı. 2004-2007 yılları arasında aynı bölümde doktora sonrası araştırmacı olarak çalıştı. 2008'de Koç Üniversitesi Kimya Bölümü'ne katıldı. Japon Hükümeti Eğitim, Kültür, Spor, Bilim ve Teknoloji Bakanlığı bursuyla Japonya Bilimi Destekleme Derneği doktora sonrası araştırma bursuna layık görüldü. Mevcut araştırma konuları arasında 2D malzemeler, elektrokataliz, hidrojen üretimi ve depolanması, fonksiyonel inorganik katmanlı malzemeler, fotokataliz, inorganik malzemelerin fotokimyasal uygulamaları, katalizörler, foto-elektrokimya, heterojen kataliz, floresan moleküler sensörler, elektrokimya, nanokataliz, nanomalzemeler yer almaktadır. Ünal halen Koç Üniversitesi Yüzey Bilimi ve Teknolojisi Merkezi KUYTAM direktörlüğünü yürütmektedir. Hocam vakit ayırdığınız ve katıldığınız için tekrar teşekkür ediyorum.
Ben çok teşekkür ederim. Sağ olun tanıtım için. Ekranımı paylaşabilirim herhalde, değil mi?
Evet, buyurunuz.
Okey, tamam. Evet, sanırım şu anda görüyorsunuz.
Başlıyor. Evet, şu anda görüyoruz.
Tam ekran geliyor mu?
Geliyor.
Tamam, okey. Okay, yes. So, okay, I'll do the presentation in English. So my name is Uğur Ünal. I am from the Chemistry Department of Koç Üniversitesi. I'm also the director of the Koç Üniversitesi Surface Science and Technology Center, KUYTAM. So I will today, I will talk about high entropy alloys and the design application of these high entropy alloys for some electrocatalytic applications. And we are carrying out this research both at KUYTAM at Surface Science and Technology Center and in my lab. So we know we have an energy problem, and then the energy sources are generally now fuel sources, so fossil fuel sources, but the renewable energy sources, the amount of renewable energy sources is increasing, and it's but still, at that desired level. But since, we have this environmental problem of increasing global temperatures, we need to increase the amount of renewable energy sources in order to reduce the increase in the global mean temperature. So otherwise, the expected global mean temperature for high emission scenario, if you do not go to renewable energy sources, if you still keep using the fossil fuels, it will be around 4 degrees by 2100. But if we can control this emission, and if you start using renewable energy sources, we are expecting to keep the global mean temperature around the change around 2 degrees. So that's why we need a strong need for alternative and environment-friendly energy sources. So as you know, the hydrogen is one of the energy sources. There's a very high energy density. It's the most abundant element. And there are many options for different production technologies. In Europe, these electrolyzers, the number of electrolyzers increasing and the capacity is increasing. In 2024, the expected capacity was around 6 gigawatts. I think they reached this capacity, and they are still trying to increase the capacity. And the hydrogen might be used in many applications, and there are many sources for the hydrogen. We can use these renewable energy sources, wind, solar, photovoltaic panels, or concentrated solar power to produce hydrogen from water. like nuclear energy, and then the batteries are also other sources. But hydrogen can be used, like the hydrogen obtained, this green hydrogen produced from these renewable energy sources can be used in many applications, many industrial applications, and in value-added applications, like in metals refining, in steel industry, in ammonia production, because ammonia is another important energy source. It can be used to produce ammonia production. It can be used to produce synthetic fuels by using the emitted carbon dioxide in air or in different sources as well. And then, like the hydrogen can be used in fuel cells or in internal combustion engines. So it's a very valuable energy source. And like there are so many studies, of course, research in all over the world to produce hydrogen from these renewable energy sources, and also to decrease the cost of hydrogen, of course, because the cost is also important. Carbon dioxide reduction is another important problem. It is also widely studied because, like, we are releasing a lot of carbon dioxide in air from different activities, like human activities. So, like now the amount of carbon dioxide generated by human activity in 2018 was like around 35 billion metric tons. So that amount didn't change much. It is still around the same amount. But like if we can produce all the chemicals from the carbon dioxide, we will be able to use around 300 million metric ton. Like if you compare these numbers, it is I mean, we still have like large amount of carbon dioxide remaining in air, even if we produce all the chemicals from this released carbon dioxide. And the cost is also huge, like around 50 to 100 per metric ton. There are so many like carbon dioxide capturing technologies in the world, but this number is still increasing, but it is not enough. So like new technologies must be developed, like cheaper technologies must be developed. So there are different ways to reduce carbon dioxide to these like more valuable chemicals, like electrochemical reduction, which is used electrical energy, and this electrical energy can come from the renewable energy sources. For the chemical reduction, which uses like readily available sunlight as well. So if we can increase the efficiency of this carbon dioxide reduction processes, and also like reduce the cost, of course we will not be able to reach to like zero carbon goals, but we will be able to at least increase the carbon dioxide significant amounts, and we will be able to convert carbon dioxide like valuable the chemicals or products. So for the hydrogen, technologies, like hydrogen is important, and as we have mentioned, like the hydrogen is used in fuel cells, for example. Fuel cells is an important electrical energy source. In addition to the batteries, it has a very specific energy density, but like specific power density is low compared to the capacitors. There are development of the electrochemical capacitors as well. And like the fuel cell, as you know, again, like in the fuel cell, we have different reactions, like hydrogen evolution reaction, hydrogen oxidation reaction, oxygen reduction reaction, and oxygen evolution reaction. And there are different catalysts used in this electrochemical processes, and these catalysts generally like the noble metals, like ruthenium, iridium, palladium, rhodium, or platinum. Like for oxygen reduction reaction, which is one of the main reactions in fuel cells, the platinum is used, and like these are all very expensive, and like abundance is low as well. Abundances of these metals are low. So we should go to the alternative catalysts like transition metal oxides. Transition metal oxides, some transition metal oxides work well for these catalytic applications, but still the efficiency is not as high as these noble metals. Like, and it's not as high as platinum or ruthenium or iridium for like oxygen evolution reaction. Like controlling these reactions are also not easy. Like the ORR reaction is quite sluggish. OER reaction is also quite sluggish. So we need to control the different steps of these reactions in order to increase the efficiency. The hydrogen evolution reaction is quite straightforward, but still, like the platinum is the most efficient the catalyst for the hydrogen evolution reaction. So we need to find some ways or some like new materials in order to decrease the use of these noble metals, or in order to decrease the amount of these noble metals in catalyst, or maybe we should get rid of these noble metals and we should use transition metals, which are much cheaper, much abundant in nature. So this is, I mean, this is the periodic table, and this is chemist tool actually. And we know the properties of all elements in the periodic table. And by using the properties of the elements in periodic table, by the rational approach for designing new materials, we can construct like new crystal structures, new energy structures. Like photocatalysts, for example, like generally this D0 and D10 metals are used in order to construct the energy structure. So the most efficient photocatalyst can be produced from this type of the elements, D0, D10 elements. And like the noble metals are used as a co-catalyst in order to increase the efficiency. And for electrocatalyst, we are using these noble metals again, like the platinum, palladium, then iridium, like where have this low deep band levels, and then they are effective in electrocatalytic applications. But like still, again, they are expensive and they are not that abundant. We should develop new technologies and new materials in order to find cheaper and more effective catalysts, both photocatalysts and then the electrocatalysts. So in my group, we are studying different materials. We are focusing on like 2D materials, layered perovskites, or single metal doped layered structures. And like recently, we start studying like this high entropy alloys as well. I will explain what it is. And we are trying to decrease the amount of noble gases by introducing these noble gases as single atoms on different structures, generally graphitic structures, or we are trying to disperse these metals, noble metals like co-catalysts, into the 2D layered materials, into the structure of the 2D layered materials to produce single active sites, which decreases the amount of noble metals and it increases the number of active sites in the crystal structures. So like we are studying photocatalytic water splitting, different electrocatalytic reactions, photocatalytic carbon dioxide reduction, and then ammonia conversion or ammonia synthesis in our group. I will today talk about the like electrocatalytic reactions or ER reactions mainly by using high entropy alloys, and I will give one example of ammonia synthesis on high entropy alloys as well. So again, as I said, like generally the electrocatalysts are metal-loaded carbon materials And like the problem, like here you see some platinum particles on graphitic material, on graphene, which is used in oxygen reduction reaction. But as you see, there are a lot of platinum in here. So this is an expensive material. It is efficient. It is efficient. I mean, the efficiency is high, but it is expensive. So instead of using such high number of nanoparticles, high number of platinum atoms, we can disperse those particles onto graphitic structure as single sites, which is still active, which is still with a very high efficiency, but the number of atoms is low in this case. I mean, these two materials gives a similar efficiency, but the amount of noble metals used in single atom introduced structure is low. Or like we can use only transition metals without any noble metals, and then produce high entropy materials, and they might be still active. So I will talk about high entropy materials. So we know what an alloy is. Alloys are like traditionally a solvent element to which various solid atoms are added for improving specific properties. So in conventional atoms, we have like one or two type of metals introduced into a matrix of a metal in a solute metal. But in high entropy metals, we have like at least 4 or 5 different metallic atoms. Like these two scientists, Professor Brian Cantor and Jean Wei, they changed the way we look at the alloys. So they produced like either equiatomic or non-equiatomic multi-component alloys, and they introduced different like the properties. So these high entropy alloys are composed of at least 5 principal elements with near equivalent molar ratios. So they might be equimolar or non-equimolar. They exhibit high configurational entropy. They have sluggish diffusion kinetics, lattice distortion, and also the cocktail effect. So like they might be, I mean, like the conventional alloys are a mixture of like 2 or 3 metals, but in high entropy alloys are the mixture of at least 4 or 5 metals. So they can be again equiatomic or non-equiatomic. So they have very high mixing entropies of solid solutions, which enhance their stability compared with interatomic compounds, especially at high temperatures, because when at high temperatures, since the entropy of mixing is high, the Gibbs free energy will be more negative. So this will increase the stability of the high entropy alloys. In order to design an alloy, high entropy alloy, there are like different approaches, like theoretical approaches. We can use the high entropy of mixing. So like as the number of atoms in the number of metallic atoms increases in the structure, entropy of mixing increases. So the configurational entropy increases, and that increases the Gibbs free energy of mixture, especially at high temperatures. Another important factor is the atomic size difference. So the critical atomic size difference in order to form high entropy alloy is around 6.6%, and it is calculated by using different atomic sizes of these elements introduced into the alloy structure. Valence electron configuration determines the structure. So for like FCC structure, we know like the metals in the periodic table, they have either FCC structure, BCC structure, or hexagonal close-packed structure. So for FCC structure, this valence electron configuration is around 8.5, But for BCC or HCP structure, it decreases to 6 and 2.8. So by controlling the valence electron configuration, we can control the structure of the final the product. The ohm parameter is also another important parameter to design the high entropy alloys. The higher the ohm value, the higher the probability of forming single phase random solution in high entropy alloys. So these are different, again, design strategies to obtain desired high entropy alloy. And when you prepare a high entropy alloy, they introduce these 4 core effects. One of them is the high entropy effect, which stabilizes the structure. Other one is the lattice distortion effect, which actually introduces different like energy sites on the surface or binding sites on the surface for different catalytic applications. So there is a cocktail effect. Like in the cocktail effect, since we are bringing like at least 4 or 5 metals with different properties, with different like orbital structures, different electronic structures, with different d band levels, this cocktail effect will introduce a mixture of these properties at the nanoscale. So we will have a composite at a nanoscale, which introduces like different properties that cannot be obtained like from single atom or like at least a conventional alloys. There is also sluggish diffusion effect. So the sluggish diffusion effect also, so since we have now lattice points with different atoms at these lattice points, we will have different lattice energies. So this will prevent the motion of the atoms. So, and then this will increase the stability of the high entropy alloys as well. So all these properties will allow us to use high entropy alloys in different applications, like in different catalytic applications. So high entropy alloys recently like used in many catalytic applications, including like hydrogen evolution reaction, hydrogen oxidation reaction, ammonia oxidation reaction, or ammonia production by nitrogen reduction, or urea production by nitrogen reduction in like carbon nitrogen coupling reactions, and also other catalytic reactions. So here at Koç University, we are producing different structures of the high entropy alloys, like thin films of high entropy alloys on some like stainless steel, for example, in order to improve the anti-corrosion properties, or in order to improve the like biocompatibility. And we are using in different catalytic reactions, like in water splitting or electrochemical nitrogen reduction reaction. So again, like in for the conventional electrocatalysts, the problem is the limitations are the scarcity, cost, and then the instability. So we are producing high entropy alloys directly on different electrodes in order to use in these catalytic applications, in hydrogen evolution, oxygen reduction, or nitrogen reduction in reactions. So we are either producing them in like nanoparticles or micro-sized particles, and then prepare ink and introduce that ink onto the electrodes, and then we are doing our electrochemical tests with high entropy alloys. So the first example is this copper, cobalt, iron, nickel high entropy alloy, and we introduced manganese and molybdenum into this structure, and then we started with metallic sources, raw materials, and then we did ball milling with these metallic sources So we got this like the plate-like morphology of these high entropy alloys. We changed the molybdenum structure, like the amount of molybdenum in the structure. Like we prepared equimolar high entropy alloys, and we decrease and increase the molybdenum structure as well, which control the structure actually. Like cobalt, copper, iron, nickel has the FCC structure, but introducing molybdenum also produces the BCC structure, which because molybdenum has the BCC structure. And then we started again with like equimolar compositions, and what we get is close to the equimolar compositions, as you see in table. So we ended up with the desired compositions after the ball milling. Of course, like introduction of the molybdenum changed the crystal structure. The structure without any molybdenum has the FCC structure, but introduction of the molybdenum introduced the BCC structure and then decreased the crystallite size of the FCC structure as well. So these are obtained from the Rietveld analysis of the X-ray diffraction patterns, and this is in accordance with the expected crystal structure from this theoretical calculations as well. So this valence electron decreased to 8, so which is for the FCC and then the BCC mixture of the FCC and the BCC structure. And then the entropy of the mixture increased and delta decreased as well. So in decreasing delta means like increased stability. So we did TEM analysis and we observed this different FCC and then the BCC structure in the structure as well. So we did EDX analysis, and as you see in the EDX analysis, all the metals are homogeneously distributed in particles. So we have this homogeneously distributed metals in the alloy. So there is no consolidation of any structure in the alloy, but homogeneous distribution of all metals in the alloy. So we did the electrochemical test. The one with the molybdenum 1.5 composition has the lowest over potential, as you see in here, and it has also it showed the highest activity. So we compared like our work with those in the literature for the oxygen evolution reaction, and we have one of the lowest over potentials in the literature. So, and then we also did the stability test. So of course the over potential decreases over time, but like that decreases very like it's not that significant. So it works. It is stable and it works for oxygen evolution reaction. And we also tried hydrogen evolution reaction, and in this case the molybdenum 0.5 composition produced the lowest over potential, and also it's quite stable. And then again, over potential decreases a little bit, but over 20 hours it is quite stable. Then we produced, and then again, this is like the over potential is good compared to the others, like similar materials in the literature as well. But of course, like the over potential is not only the property to show the activity of the electrocatalysts for this kind of electrocatalytic reactions. So we did like TOF analysis. So the molybdenum 1.5 composition has the highest turnover frequency. This is showing that it is also like the intrinsic property is also good. So like independent of the area and the amount of material, intrinsically it's a good electrocatalyst. And electrochemical active area is also increased by introducing molybdenum into the structure. So then we constructed the whole cell, complete cell, by using molybdenum 1.5 composition and then the 0.5 molybdenum 0.5 composition, and then we tried the overall water splitting in the cell. So the charge voltage is around 1.9 volts, and the Faradaic efficiency is around like 85, close to 90%, and it, like the measured hydrogen amount is close to the theoretical amount, and as you see, the cell voltage like decreases in this case, but over like 100 hours, it is actually 100 minutes. It is actually quite stable, and it produces the hydrogen and oxygen at the same time. So it works well as an in overall water splitting reaction. So again, like the molybdenum effect of the molybdenum content is obvious. So the increasing the amount of molybdenum increases the strain and then the stress on the surface, which increases the number of active sites at the surface. So that decreases the over potential both for oxygen evolution and then the hydrogen evolution reaction. So these two, like lattice distortion, is the main effect for the electrocatalytic activity, increased electrocatalytic activity. So like in a conventional BCC alloy, there is no lattice distortion, but when you introduce like 5 or more metals into the structure, like in either in BCC or FCC structure, since we have now the atoms with different sizes at these lattice points, this will create a severe lattice distortion, and also like the binding energies between different atoms are different. So the atom with closer interaction or better interaction with another atom will increases the activation energies, so that will increase the electrocatalytic activity. So, and also like introducing like more than 1 or 2 atoms into the structure will prevent the diffusion as well. So this will increase the stability of the structure. And like in an electron transported in an alloy without any lattice distortion, since there is no scattering points, this electron transfer might be easier, but in a highly distorted multi-component alloy, that electron transfer might not be easy. So that there might be localized states arising due to the interaction between these different atoms, and as a result of the distorted lattice as well. So this like severe lattice distortion will may increase the mobility of the charge carriers. And that will increase also the number of active sites at the surface, like those, and then that these active sites so will increase, and the material will be able to like work for this electrocatalytic application. In this case, it is like water splitting reaction, and it will work for electrocatalytic application. So then we since size is important here, so you have used that micron size particles in that previous example, and then we tried to increase the size of the particles by doing pulse laser deposition, and this is also a direct synthesis of the thin films of high entropy alloys from bulk materials. So we again ball milled, then consolidated the high entropy alloy, and then we have a similar structure here again, and then we have this high entropy alloy target, and over there we use this UV pulse laser, nanosecond pulse laser, and this pulse laser etches the atoms from the surface of high entropy alloys, and then deposit these atoms on the surface of the electrode. So this we have deposited these high entropy alloy thin films by using pulse laser deposition, and then we use these electrodes in our electrocatalytic applications. So this again give like an FCC structure in addition to like the BCC structure, and then we have like more porous like structure and nano-sized particles, as you see from this like electron microscope images and also from transition electron microscope images. And as you see also, we have homogeneous distribution of all metals in the structure according to this EDX analysis. We did electrochemical surface area analysis. So introducing high entropy alloy. So of course this will be an oxide form because pulse layer deposition is in open air, and like during the pulse layer deposition, the local temperature increases and that oxidizes the material. So we did this electrochemical surface area analysis. So the electrochemical surface areas for the high entropy films are high compared to the bare graphite electrode surface, and also the surface resistance is low according to this impedance analysis. So the high entropy oxide, I will call it high entropy oxide because now it's oxide, like nano-oxide and high entropy oxide nanoparticles. The Uğur potential is like around 300 millivolt. It is much lower than the previous example. And this is like the before the stability, and then after the stability, it even decreases to 200. After the stability test, it even decreases to 260 millivolts for the oxygen evolution reaction. And compared to the ruthenium and then the iridium, it is much better. And the TAFEL plots are also low compared to the iridium oxide and the ruthenium oxide samples, and it is again like highly stable. Like you see, there is like 100-hour stability testing here at 10 milliamps current density, and it is quite stable. Like ruthenium and iridium oxide samples are not stable. And then we introduced graphitic oxide, reduced graphitic oxide, to increase the conductivity at between the grain boundaries in the high entropy alloys, because the reduced graphene oxide is an it's a conductive. It's not as conductive as the graphite, but it is conductive. So we did in this case pulse laser treatment. So we used femtosecond laser. We disperse graphene oxide in ethanol, and then we use a femtosecond laser, and then we add high entropy alloy, ball milled high entropy alloy nanoparticles into the solution, graphene oxide ethanol solution, and then we did pulse layer deposition. So this pulse layer deposition produces nanoparticles of the high entropy alloys on the surface of the graphene oxide. And also, in another approach, we did ball milling. We mixed the high entropy alloys with the graphene oxide and ethanol, and then we ball milled. And this also produces the high entropy alloys on the surface of the graphene oxide, and it reduces the graphene oxide as well. So these are the TEM images of the graphene oxide and high entropy alloy nanoparticles introduced graphene oxide structures. So here you see the ball milled reduced graphene oxide with high entropy alloy, and then we see the high entropy particles on the surface of the graphene oxide. The pulse laser deposition. So these are the spectrum of the pulse layer deposition and then the ball milled graphene oxide together with the high entropy alloy. The ball milled graphene oxide reduces the ball milling reduces the graphene oxide better than laser deposition, because this is probably higher temperature in the ball milling, although it is in ethanol. I think the higher temperature will help the reduction of the graphene oxide, and as you see in the XPS spectrum, the ball mill graphene oxide reduced more than the pulse laser graphene oxide. And we again deposited these on electrodes and tried the oxygen evolution reaction. And as you see, the ball milled graphene oxide showed lower over potential compared to graphene oxide. That black one is the graphene oxide, and this blue one is the blue line is the laser reduced graphene oxide. And these are high entropy introduced graphene oxide. So the ball milled graphene oxide and laser reduced graphene oxide showed lower over potential compared to the graphene oxide or high entropy alloy. And they have also lower Tafel plots as well, which shows that they have higher kinetics on the surface of the laser in the laser reduced graphene oxide with high entropy alloy, and also ball mill graphene oxide with high entropy alloy. And they are stable as well. So this 100-hour stability test shows that although lower potential change a little bit, they are quite stable for 100 hours. And the impedance spectrum is also showing that introduction of the high entropy alloy and reducing graphene oxide by laser reduction, and then the ball mill decreases the surface resistance of the electrodes. And then we introduced boron into the high entropy alloy structure, because boron, the size of boron is small, and boron might go either into the interstitial sites or might substitute some of the atoms in the high entropy alloy structure. So the boron atom addition might increase active sites. So of course, it might increase the synergistic effects. So it might increase defects actually. So it may create some Lewis sites for improved surface absorption of the oxygen evolution reaction. It will produce defect formation, especially if it is introduced into the interstitials. And it might promote the formation of the metal hydroxides during alkaline water oxidation. So the introduction of these defects might increase the number of vacancies, and then it might increase the lattice defect, and then they might result in the improvement of the electrocatalytic activity together with the synergistic effect. So again, we used the ball milling method, the mechanical alloying method, in order to introduce boron into the structure. So we mixed again metals together with boron, and we ball mill it, and this also produced these planar structures. And this we again, since we have also molybdenum in here, we also obtained the mixture of FCC and then the BCC structure. The introduction of the boron decreased the crystal size. So these are again obtained from the Rietveld analysis of the X-ray diffraction pattern. So the introduction of the boron decreased the crystallized size, from 52.6 nanometer to 2.5 nanometer for the FCC, and from 900 nanometer to 13.3 nanometer for the BCC. And it increased the strain also a little bit, as you see, for both FCC structure and then the BCC structure, which is then expected and then the desired property. So the boron doped high entropy alloy exhibited much lower over potential to non-doped high entropy alloy, as you see, and then The Tafel plot also low for the boron doped one, and our potential, the stability is quite high. So we did like 48-hour stability, although there are fluctuations, it's quite stable. And again, boron doping decreases the resistance of the material according to the impedance spectroscopy analysis. So we also work with a group, a computational group, and then they did some computational analysis for us. So the boron, substituted boron, decreases the formation energy of the high entropy alloy. So this is for the FCC structure. This is showing that the substituted boron is more stable than the boron going into the interstitial sites. So we have the same observation for the BCC structure as well. So the energy, formation energy of the substituted boron is much lower than the interstitial boron. And also for the we had this hydrogen and oxygen absorption energies for both for boron doped and non-doped structures. So the hydrogen absorption energy for the boron doped structure is much higher than the non-doped structure, which is also showing like in accordance with the experimental observations. So we used high entropy alloys also for ammonia synthesis. So ammonia, again, is another important chemical because it has a very high hydrogen density. It can be used as an hydrogen source, like the thermal conversion of the ammonia produces like hydrogen, so its gravimetric hydrogen energy is quite high, and volumetric hydrogen energy also. So its position makes it is an important chemical as a hydrogen source. It is easy to liquefy, easy to store and transport. It has well-known production technology, and it can be used as a fuel. Like it can be used as a fuel in internal combustion engines. Like it can be used as a hydrogen source, and it is a very important chemical in agriculture industry as well, since it is used in fertilizers. And there are also like an ammonia fuel cells, so it's a very important environmentally friendly chemical as well. So we used this high entropy alloy, again molybdenum molybdenum high entropy alloy for ammonia synthesis. So we have again prepared these samples with ball milling, mechanical alloying, and use this H cell, and then tried the nitrogen reduction. So we bubbled nitrogen and applied different potentials on the high entropy alloy, and then measured the amount of ammonia by some spectroscopic techniques. And the ammonia yield is the highest at minus 0.05 volt, and at this potential, the Faraday efficiency is also around 80%. Because since we are at negative potentials, it is competing with hydrogen evolution reaction as well. But for the ammonia, the ammonia synthesis, the Faraday efficiency is 80%, and it is producing around 80 micrograms per hour per milligram catalyst. And it is quite stable, as you see as well, like at 0.05 volts. The current density didn't change, and then the activity didn't change over around 100 minutes. So this is also the last application that I showed. The most of this work was carried out by Hüseyin. So he's doing the synthesis and all the electrochemical reactions, and we are carrying out this research at both at KUYTAM and in my research lab as well. We are looking for, of course, new students that might be interested in such kind of research. So we have this new Koç Üniversitesi Hydrogen Technology Center, and then in this Hydrogen Technology Center, we are working on different hydrogen technologies like electrolyzers, fuel cells, in addition to carbon dioxide reduction and nitrogen reduction technologies as well. So if you're interested, if anyone interested in this kind of work, you are all welcome. Thank you very much for listening. And if you have any questions, I will be happy to answer.
Thank you, hocam. Now Q&A session is open. You can ask directly or you can use chat box.
Hello. So I'm Ejal. Can I speak? Can I ask question directly?
Yes, of course.
Yeah, okay. So I'm from Şişecam, from Şişecam Research Center. So it's very interesting topic for us because I'm basically currently I'm working on high entropy alloys, sputtering of high entropy alloys for some of our applications. So for sure we are not producing the high entropy alloys, but we get them, we buy them from somewhere from the United States. But to have this ability very near to us, it's very important and very good opportunity for us because we want to, as a starting point, basically we want to use this high entropy alloys to improve the corrosion resistance of our loading products. Because in our loading products we are using it's well known, so I can say we are using nichrochrome or nichrochrome oxide as a blocker layer to protect the silver in our loading stack. So we are very eager to change this material with some other materials basically. Some other materials, so one of them is the high entropy alloys. So we did a lot of research. Research means so we don't have ability to make this combining these materials and creating our high entropy alloys, but we search the material producers and we get 6 different targets, 2-inch targets from United States. This is from bigger material, basically the pronunciation is correct. So this materials containing nickel and some other as you mentioned, but I can say that we are very open and we are very interested in working on and testing these materials in our loading stacks. As we are doing also this chemical tests, the polarization measurements, polarization resistance measurements to see the corrosion behavior as a chemical point of view, and latest point we will put them in low stack, basically low stack to make another standard tests basically. So if you are open, we are very eager to. We are very open to work together and to test this material, but we need for at that point we will need 2-inch targets because one of the system we are used to it, and also you are using as I see you are already doing pulse laser deposition and using targets. I guess.
Yes. So yeah, I mean we are open to any collaboration. So I mean this is the electrochemical electrocatalytic study that we are doing on high entropy alloys, but we also deposited like different kind of high entropy alloys for like on implants, for example, for biomedical applications. So and then it improves the corrosion properties. I mean, like addition of silver, for example, we add silver and that improved the antibacterial, they introduced antibacterial effect on the implants, and like we have many like examples actually. So this is only the electrocatalytic part, but we can produce our own targets by using spark plasma synthesis technique. So we can consolidate the particles, and then we do like pulse laser deposition we are using some other vacuum techniques like physical vapor deposition to coat these high entropy alloys film on different structures.
Yeah, correct. The second point, maybe this is for corrosion part is the first point, but in the second part, we have the idea to use this new materials as an anti-scratch material. So
Yes.
I guess that would be also very interesting because
Yes.
we want to use as a top layer for our products.
Yes.
Instead of other ones. So this will be the second part, but we can also do this in parallel.
Yeah, we have also some materials for very high, like mechanical properties with very good anti-scratch properties.
But at that point, I forgot to say that this one should be more or less transparent material, but need to be oxidized or nitridized because otherwise for lobbies it would not be too applicable.
Yes. Yeah.
I'm not sure if it is also possible.
Possible. We also produce nitrides, like high entropy nitrides.
Oh, perfect.
Yeah, this is like I show one example of borides, but we also produce high entropy nitrides.
Okay, the transparency or absorption is normal.
We haven't, I mean, we were not interested in the transparency, so we haven't measured any like transparency or reflection of these high entropy alloys, but we can work on it.
Uğur Hocam çok teşekkür ediyoruz
Ben çok
vakit
teşekkür
ayırdığınız
ederim.
için ve bu harika sunum için. Değerli katılımcılar, size de çok teşekkür ediyoruz. Önümüzdeki hafta Nano Open'da Southampton Üniversitesi'nden bir konuğumuz olacak. Steve Beebe. Tekrar çarşamba günü 11'de görüşmek dileğiyle. Hocam hoşça kalın.
İyi günler, çok teşekkürler.